combinational logic circuits. Why do we study the combinational logic circuit? This combinational logic circuits play a very important part in designing day-to-day electronic circuits like adders, subtractors, multiplexers, decoders. So let's study the combinational logic circuits in detail, the working of the combinational logic circuits, and what are the applications we can design or what kind of circuits we can create using this logic circuits. So what are the overviews of studying this subject or the combinational logic circuits? Let's say the examples of combinational logic circuits are binary adders, binary subtractors, binary multiplexers, decoders, and binary multipliers. This binary adders and binary subtractors again are of two types. They can be classified as half subtractors, half adder, full subtractors, and full adders. So let's study in detail the application of combinational logic circuit, starting with binary adders. So before this, the learning objective of combinational logic circuit is to explore the Boolean algebra in design of electronic circuits. Each type of gate implements a Boolean operations. That is, using this combinational logic circuits, we can simplify various kind of Boolean expressions. We can implement various kind of arithmetic operations like adders, subtractors. Plus, the most advantage of this combinational circuit is that they are memoryless. That is, they don't require memory. They work only on the present inputs, and it has no concern with the past output or the past values what have been used. This is the example of combinational logic circuit. Combinational circuit consists of logic gate whose output depends on the present inputs. As I've said, it doesn't have any memory element. That is, it contains the output which depends only on the present input. This combinational circuits have various kind of gates included in it, like XOR gate, XNOR gate, then AND gate, OR gate, and so on. As the topic advances more and more, we can discuss the applications of the gates which are used in combinational circuits. So the first is half adder. A combinational circuit that performs the addition of two bits at a time is called full adder. As the name itself implies, the adder, that is, it adds the two. The input variable designate the augment and addend bits and produce the output as sum and carry. That is, let us take this with the example of this circuit, which is the circuit diagram for half adder. So this is the truth table. I'll be working out on how the truth table works for half adder and half subtractor. So before this, let's see roughly or precisely the truth table. These are the two inputs, AB. These are the inputs. Let's say various combinations of inputs are 0, 0, 0, 1, 1, 0, and 1, 1. Okay. So as we know the addition, 0 plus 0, that is 0. To explain this, I'll work out, let us say, for half adder. The circuit diagram for half adder is shown here. That is, here we use XOR gate. To explain this, the working of half adder, let us take the circuit and how the working takes place. This is the circuit diagram for half adder where it gives sum and carry. Now, let us take output as A, B. The variations are 0, 0, 0, 1, 1, 0, 1, 1. One output will be for sum and the other output will be for carry. That is, 0 plus 0, the sum gives 0 and the carry is 0. 0 plus 1, the sum is 1. Since there is no carry, the carry is 0. 1 plus 0, the sum is 1, and again no carry, so 0 carry. 1 plus 1, the sum again is 0 and the carry is 1. So if we take the K-map for this, that is if we try to find the equation for the sum, we can take it as AB, which will be 0 1 0 1. This A bar A, B bar B. The sum is 1, that is for this will be 0 0 1 2 3. That is the sum is having output high for 1 and 2. Sum is having output low for 0 and 3. So output high for 1 and 2. So to take the equation for this one and for this one, the equation for sum will be A B bar for this and plus A bar B. That is equation for sum is A X or. Similarly for carry, we can see carry is low for 0 1 2 and high only for 3. So we can take the K-map as A B 0 1 0 1. That is the equation will be, this will be 0 1 2 3. That is the output is low for 0, the output is low for 1, the output is low for 2, output is high for third. That is the equation for carry will be, this is A bar, this is A, this is B bar, this is B. So the equation for carry will be AB. To have a better understanding of how the adders work or how the subtractors work, let us have some basic idea about the K-maps. So roughly I'll be explaining about the K-maps, how the K-maps work, what are the explanations or how the K-map output can be obtained. So we'll study K-maps for two variables, that is A and B. Let the K-map equation, that is the minimum equation y, is given by sum of m 0 to, okay. So K-map for two variables, that is the first variable will be A, the second variable will be B. Now as we can see, the K-map is having 0 1 2 and 3. So before writing down the equations, let's check out how the values can be found out. This is 0, this is 1, this is 0, this is 1. This sum of m, this represents SOP form called as sum of products, and if it also called as min terms, and it is represented by 1. So if SOP term, sum of product or min term is given, we always represent the min term by 1. Similarly, if y is given like this, pi of m, say the values are 0 to 3 for two variables, well, it is called as POS, that is product of sum, and represented by 0. So this value is written as 0, this is 1, this is 2, this is 3. Since this is 0, we write it as 1, represent 1. 1 because it is a summation pi SOP term, and SOP is always represented by 1. Now there is no 1 written here, so we write it as 0. It is 2, that is 2 is having a value, so we write it as 1, and 3 here, so we write it again as 1. To find out the equation, we group ones in such a way that no single one will be alone. If possible, the groups can be done. So this is first group, this is group number 1, and this is group number 2. Okay, so A represents, since this is 0 represents, and this is here A, so it is A bar. 0 is always represented as bar and 1 is represented as A. Similarly, this section is for B, so 0 represents B bar, 1 represents B. So the output for this equation will be for this equation, that is for group number 1, A bar and A. Here A bar and A, that is both are there, so A bar and A gets cancelled and the output remain here only is B bar, that is B bar. Similarly for this group, B bar and B gets cancelled and the output remains A, that is A. So the final output will be A plus B bar.